Hi everybody, today we're going to design and build a small 5 volt reference standard which has an accuracy of 0.01% or better. And the reason behind this is I wanted to design a little unit which is easy for the hobbyist to make. It is very accurate, it needs no adjustment, and it has additional features such as auto switch off, a little battery monitor circuit there, and simple to build. And the whole cost of this project will be around £10. So let's have a look at how we're going to go about this today. Well, here you see the circuit I've put together for this project, and the heart of this is a small IC manufactured by Intersil. It's a 5 volt reference IC, but it is very accurate to plus or minus 0.01%, and it has a temperature coefficient of 3 parts per million. So the heart of our circuit is this IC here, which is the ICL 21009 BFB850Z. Now it's important that this is the one you get because Intersil make a number of variants of this IC with different specification. This is the highest specification, which has a accuracy to plus or minus 0.5 of a millivolt, which equates to plus or minus 0.01% error, and 3 parts per million degrees centigrade. Now these ICs will cost you around £7, so they're not too expensive, and they require no adjustment. Even though there is a trim facility on pin 5, you need no adjustment on these ICs to give you the accuracy I've quoted here. Now, as you see here, the reference IC needs very few components for it to function. Just a few capacitors here. You have 2 capacitors on the input there on pin 2 with a voltage in, a 0.1 microfarad and a 10 microfarad. The 10 microfarad I'll be using will be a little Tantulum capacitor, probably a 16 volt working one. And the output voltage comes out on pin 6 of the IC. That's the reference voltage out, and we have a little decoupling capacitor there just to filter out any noise, and we only need a small value there, 0.01%. You don't need a large value there because it will affect the output voltage in terms of its rise to 5 volts at switch on. So that basically is the reference circuit there, not a great deal to it. The input voltage on these ICs does have a wide range. We're only supplying 9 volts of this chip, but you'll find that if you look at the data sheet for this IC, it does have a wide input range. We just have a quick look at the data sheet for this 5 volt reference IC which we're using. It's the Intersil ISL 21009. So this is the details about this particular IC. One interesting point is that it does actually have this wide input voltage range, anything from well, as low as 3.5 depending on which chip you get, all the way up to 16.5 volts. Now this particular voltage reference IC comes in variances of voltages. You can get it from 1.25, 2.5, 4.096 volt and 5 volt. We're going to be using the 5 volt version, and we're going to be using the highest tolerance 5 volt version of this IC, which has a 3 parts per million degree centigrade temperature coefficient. So you'll see here that the IC we're using today is the third from the bottom on this list here, which is this one. Now, as I say, the voltage supplying this reference module today will be a standard 9 volt PP3 battery, as we see here. And rather than have a simple on-off switch, a toggle on-off switch, I'm going to have an auto on-off feature on this particular unit. And to do that, I'm going to use a P-channel MOSFET, and that is going to be triggered simply by a little tactile push-button switch. Now the MOSFET I'm going to use for this little circuit is the IRF 9630. The reason behind that is that they're very cheap to buy, and it has an on resistance of less than 1 ohm, which is ideal for the switching circuit we want to use here today. Now the way this little circuit works is quite simple. Under normal conditions the MOSFET is open circuit. Even if you supply 9 volts to the source of the MOSFET, it will be open circuit, and therefore nothing's coming out to the reference IC. To turn the MOSFET switch on, we need to provide a negative voltage onto the gate of the MOSFET. That's negative with respect to the source, and the way we do that is with the little tactile switch here and these few components. So the battery is powered permanently. Immediately we press the little button, just for a second, it closes that switch there and connects the 1K resistor to ground. What then happens is, very quickly, the 10 microfarad capacitor there charges, and it very quickly charges up to the, well, not quite 9 volts, but it charges up to a voltage. And once that button is released, that is now open circuit. However, we have a negative voltage on the gate of that MOSFET with respect to the source, so that charge on the capacitor is effectively turning the MOSFET on. So the MOSFET now switches on and supplies the 9 volt supply to our reference IC. Now what happens is that the 10 megohm resistor we have across that capacitor slowly discharges that capacitor, and the timing of that circuit there, it takes about 2 minutes or thereabouts before the voltage there drops so low that the MOSFET then switches off again. So effectively we have the auto switch off, which means that there's no danger therefore now of leaving the unit switched on and draining the battery. So simple circuit, but supplies the voltage supply to our circuit. Now the other circuit we have on this today is a little battery monitor circuit I've put together here, and the reason for that is that because we're using a standard 9 volt battery in an enclosed box, we need to know when to replace the battery. Now what I've done here is used a combination of a dual LED and a couple of Zener diodes to give us that indication, and the way this circuit works is quite simple. The LEDs there, they have a common cathode on the LED, and the anodes you drive then up to the positive supply. So if you look at the green LED, we have a 1K resistor, which is a current limiting resistor, in series with a 5.6 volt Zener diode. And these particular LEDs, they need around 2 volts or a little bit more to operate these LEDs. And if you think about it, we have a 9 volt supply under normal conditions. So if you have, say, between 2 and 3 volts across the LED, then you add that to your 5.6 volts and you're approaching our 9 volt supply. So as long as the voltage there is 9 volts, current will flow through the Zener and the 1K resistor, and there'll be sufficient voltage to operate the green LED. So switch on, the green LED comes on. If for any reason the voltage from the battery were to drop, you can see here, if it were to drop down to 5.6 volts for example, then all that voltage will be dropped across the Zener. There'll be nothing across the LED and the LED would be out. But in reality, because the LED needs a few volts anyway to operate, you'll find that when the voltage on the positive supply there gets around 6.5 volts, then there's insufficient voltage coming down here to turn on the green LED. So then that turns off. Now if we have a look at the red LED, you'll see we have a similar arrangement here, but no Zener in that path. We have a current limiting resistor supplying the 9 volts to the red LED. Now under normal conditions the LED would have been alight, but we have a transistor here connected from the anode of the LED to ground. Now this transistor here is normally turned on when the battery voltage is normal, and the reason for that is that you'll see we have another 5.6 volt Zener there. So we have 9 volts there, we have the current flowing down through a 5.6 volt Zener to the base of the transistor, and as long as the voltage there is great enough to overcome the voltage of the Zener and the resistor network here, you'll find you have sufficient voltage on the base of that transistor there to turn the transistor on. If the transistor is on, it connects that point there to ground, and therefore the red LED would stay off. If now we assume that the voltage here were to drop down to say 6.5 volts or thereabouts, we've already explained that the green LED would go out. Now what happens is that as soon as the voltage there drops, you'll find that because we've got the 5.6 volt Zener there and the resistor chain, this voltage here will drop low to such a point where this transistor then switches off. As soon as the transistor switches off, it allows the red LED to be supplied with current through the 1K resistor, and the red LED comes on. So that's how our little voltage monitor circuit is working. Quite simple but quite effective. Now that you will find that there is a slight crossover point when it switches from green to red, so you'll find the green one will go very, very dim and the red one will come up just dimly, but there's a switchover point between the two, and that's round about 6.5 to 7 volts. Now one final little point about this circuit is that when the unit powers off, goes to auto power off, you'll actually find that you'll get a little indication on the red LED as well. So it also gives you a warning that the unit is powering down, which is also a little nice feature of the unit. So there we have the circuit. Well, what we'll do next is we'll build this circuit on a breadboard and test it before we actually build the project onto a little prototype board and build it into a box. Right, here we have the components for our project today. A little project box again, 83 millimeters across, 53 that way, which is the height, and then the depth of it is 35 millimeters. It comes with a aluminium top, which we'll actually go into use today and cut out our inputs on the top there. There we have a PP3 battery holder, the 9 volt battery holder with flying leads, and a standard 9 volt Duracell battery. There's 5 1K resistors, and there's a 1 10 megohm resistor. Here we have 2 4mm banana sockets there. You can choose whichever you want for the project. These are reasonably good quality ones with the gold plated, but you can use some cheaper ones if you find them. There's a small electrolytic capacitor, which is a 10 microfarad capacitor. You'll notice there that one leg is longer than the other. The longest leg of the wire is the positive. There is a small Tantulum capacitor there, 10 microfarad Tantulum capacitor electrolytic. Again, the longest lead is the positive lead. And then here we have a couple of small capacitors. This one here is a 0.01 microfarad, and this is a 0.1 microfarad. There is the 2 5.6 volt Zeners. These particular ones are 1.3 watt Zeners, but you can use lower wattage Zeners if you wish. I think you can use some 500 milliwatt Zeners. Here is the P-channel MOSFET, which we're using for the auto switch on and switch off. That is the IRF 9630. And here we have a standard NPN transistor. The one in question here is the 2N3904, which is just a general purpose transistor. There is the little PCB board, which is a little converter board, adapter board, to allow us to put the reference chip on, and then we have the pinouts more accessible. There's the reference chip there, which comes in a SOC passage, SOIC package, 8-pin. Not too small, this one, so it's relatively easy to solder onto the little adapter board there. And here I've made a little template. You can see I've got a few crosses on there for the holes to be drilled, and I'll use that as a template to mark and drill the holes, and then I'll stick that on top afterwards as the sort of front panel display there. It's self-adhesive on the back. Just peel off the back and it's self-adhesive sticky on the back. Now this particular project box we're using, just take the lid off, it's got a project board, matrix board inside the box. and in fact if I just lift it out, on the reverse side of the project board you've actually got some solder connections, but they're all independent, so you can strap them up as you wish for the particular project. So we'll be using some of that to anchor components down today, and I'll show you how we're going to position the components. And then inside the box there's fixing screws and some little rubber feet which we can put on the bottom of the box. So just a quick look at a few of the components I mentioned earlier on. One thing I forgot to mention was the fact that I'm using a small tactile push button switch there with a little push on knob. So that's the tactile switch there. Just a point about the LED and the MOSFET. The LED is what they term a tricolour LED. This one's a red-green, but obviously you can have red, green, or you can have them both on together. That's why they call it tricolour. The centre lead there of the LED, that is actually the cathode, and that's the longest lead, and the next longest lead there is the red LED anode, and the shortest lead there on this side is the green LED anode. So that's green LED anode, centre one is the common cathode, and the other lead there is the red anode. Now the MOSFET here, the pin out connections on that, the way it's positioned at the moment as you view it, the pin there is the gate, the centre pin is the drain, and then the pin on this side is the source. So that's how you would wire it up. Right, I just thought I'd show you how I go about soldering this small SMD reference IC onto this little adapter board. The board itself is sort of multifunction. You've got different sort of size on that side to the other. We're using the larger side, which is quite nice today because it's easier to solder on this, the slightly larger version. But I would point out that on the board itself you'll find that the inline pins down the side there, pin 1 is marked there, there's a little 1 on the board, and then on the actual pads on the board you find you've got a little white dot just there, and the white dot that's pin 1 there on the board. So we have to match that pin, that white dot, with the dot on the chip, which is pin 1. So when you look at the chip you have a little indentation next to the pin number 1. Now before we solder it onto the IC, what I normally do is just use a flux pen and then just go over the board with a flux pen. Now the next little tip I find is that you want obviously this to remain absolutely still when you're soldering, so I find it easy to use a bit of blue tack. So positioning the board on the blue tack there, it holds it firmly in place while you solder. I'm now going to position the chip on the board itself, and as I say, you have to make sure that the little indentation there on the chip is against the white dot there on the PCB. So we just need to line it up. Once it's lined up, just press it down firmly. You'll find that the flux we put on from the flux pen is a little sticky, so it tends to hold it in place. So that will hold it in place there now. And the first thing to do is just tack one pin of the chip to one of the corners. And the solder I use for that is some very fine solder. Also make sure you have a pointed tip on your soldering iron and try and keep it clean. Then basically what you do is hold the tip of the iron on the pad, not on the IC, on the pad of the adapter board there next to the pin, heating it up, feeding the solder on, and then that's tacked that one pin there. Once you've got one of the pins tacked on, then we can go around and do the other. So I'll just go around and do the other pins now. Right, that looks quite good. Just a little tip, if when you're doing this you have some problems where the solder flows onto two pins, one quick way of recovering from that is to use some solder braid. There's this type of stuff, and just hold it onto the pin and heat it with your solder iron, and it'll draw off any excess solder in between the pins. Just as a matter of interest, this is the solder here that I've used today. It's very fine. Also, this particular brand from Multicore sets at a particular temperature, so once you solder it and remove your iron, it's set straight away. Right, the next thing we're going to do is solder some inline pins in on the adapter board there. An easy way to solder the pins is to use a breadboard and pop the pins in and then plug it onto the board with the correct spacing. Then use a flux pen just to put a bit of flux on the pins. And then again use some fine solder. Right, here you can see now I've laid out the components on the breadboard so we can test the circuits. Basically we have the main reference chip there, the voltage reference chip, and its associated capacitors there. The output capacitor there is the 0.01 microfarad, and the input capacitors are 0.1 and a small 10 microfarad Tantulum capacitor on the input. The voltage feed to that is the red wire link there, and this is the P-channel MOSFET which we're using as the auto switch on off feature with its associated components. So you have the 10 mega ohm resistor there, 10 microfarad capacitor, the 1K resistor down there feeding the tactile switch which triggers the MOSFET to switch on. The red wire here is the 5 volt reference output. That's the common earth wire, and this red wire here is the voltage in from the 9 volt battery. Now the rest of the circuitry here is the voltage or the battery monitor circuit, and we have the bicolour LED there, which is a red-green LED with common cathode. We have the two 5.6 volt Zener diodes there. There you see the NPN transistor, general purpose one, 2N3904, and there we have the four 1K resistors. So that is the basic circuit which is monitoring the battery level, and the LED would then indicate either red or green depending whether the battery is okay or not. Now when you wire this circuit up finally, you need to make sure that your earthing connections are really going more or less to the same point, but obviously on this breadboard we can't do that, so this is not ideal, but for the purpose of testing the circuit it will be fine. So let's now connect the breadboard up to some power and look at the voltage out and the current actually that it's drawing when we're using the unit. I've just hooked up the breadboard there that we've laid out the circuit on, and I've just connected it up to the test meters. These are the connections going to monitor the output voltage from the voltage reference. I'm also going to monitor the current that it's taking on the input, and I'll connect it to a power supply, bench power supply first of all, to check the operation of the LED there. So let me just zoom out and we'll have a look at the board and the test meters measuring the output and the input current and the power supply feed into it. Right, now here we have the breadboard with the circuit on. It's connected now to the output reference voltage. It's connected to this meter here, so that's going to monitor our 5 volt reference. This meter here is going to monitor the input current, the current drawn by the whole unit. And then I'm going to use for the moment the power supply here in place of the 9-volt battery, so we can demonstrate the effect of the battery going low. But what we'll do first of all, we'll set the power to the unit to 9 volts. So we have, as though we had 9-volt battery connected. So I'll select 9 volts, and then I'll switch the power onto the unit. So there we have the 9 volts there coming out now to the unit, but the unit is switched off. So there's no current really being drawn from the unit, and there's nothing coming out on the output voltage. If I then just briefly press the little tactile button there, the unit should turn on. So I'll just press that and let go. So now what you see is the LED is glowing green, and the output from the reference IC, the 5 volts, is now showing here on the meter. So we have 5.0001 at the moment. The current that's being drawn by the whole of the unit is 13.7 milliamps, and the bulk of that current is really taken up by the little voltage monitor circuit here on the board. So if you didn't want the voltage monitor, you could remove that, and you would probably find that the current would go down to around about only 1 milliamp. Now the unit will stay on for about 2 minutes having pressed the button, and the 2 minutes, as I mentioned when I discussed the circuit, is the time constant of the capacitor and the resistor there on that MOSFET. So as the capacitor is discharged, eventually the MOSFET will switch off, and then you'll see the circuit will disconnect from the power supply. When that happens, you'll notice that the green LED will turn red briefly, indicating the voltage has first of all gone low, and then it will fade and go off altogether, so it's disconnected from the power supply. So this is about 2 minutes, and we'll just wait and just watch and make sure that the unit now turns itself off in the auto off mode. You can see there the voltage is steady now. Now you see it's switched off. You see the LED is now turned red. The red glow fades as the voltage goes completely, and the unit is now turned off. So the reference voltage is dropped away, and the current drawn by the unit is just going down to zero, dropping down to zero as the MOSFET now completely turns off. Well, we've got the module connected up. What I want to have a look at is what the current draw is if you disconnect the little voltage monitor circuit here. So what I'll do, I'll just temporarily remove the voltage supply by removing that, disconnecting that red wire there. So that's removing the voltage supply from this circuit here, but the voltage reference circuit and the auto on circuit will still be functioning okay. So now when we press the button to turn the reference voltage on, you'll see we immediately get the reference voltage coming out there. That's going now up to the 5 volts reference. You'll see that now, and if you look at the current that the unit is now drawing, it is in fact 0.1025 of a milliamp. So it only draws really around 100 microamps if you just want to use this part of the circuit on its own. Very, very little current drawn. And you see there that the reference voltage out at the moment is reading 5.402. I've just reconnected now the supply wire there to make sure that the voltage monitor circuit is working again, so it's back to normal. And this time what we're going to do, I'll trigger the circuit again by pressing the button. At the moment we have the voltage on the input going into the board at 9 volts, and this time we'll have a go at just reducing that voltage and seeing the effect it has on the circuit. So let me just switch it on, press the button. Again, immediately I press the button, the LED there turns green, and you can see that the reference voltage there is 5 volts coming out, and the current drawn by the unit is 13.7 milliamps. Now what I'll do this time is I will lower the voltage going to this board from 9 volts to 8 volts. So there we have 8 volts now going to it. No effect at the moment, the green LED is still green. We've still got 5 volts coming out. The current has dropped slightly. If I lower it now down to say 7 volts, and now what you see is that the LED has virtually gone out and the voltage has just dropped slightly, but really it's still around about 5 volts. The current has dropped down to 8.1, 8.2 or thereabouts. If I drop it now down a little bit further to 6.5 volts, 6.5 volts. Now this time at 6.5 volts you'll notice here now that the LED has turned red, and that's simply indicating low battery, and that's the time to replace the battery. And again, the voltage still coming out of the reference chip is still fairly close to the 5 volts reference, certainly within tolerance there. I'll just take it back up now to 9 volts. So there we're back at 9 volts there. The LED has now gone back to green, but shortly we should see the unit power off in auto power down mode. There we are. The unit is now turned off. The LED turns red for a brief second, and you can see the unit is now powering down. The voltage is dropping on the reference voltage, and the current is also dropping. It'll drop down to 0. So the unit is now turning itself off. So that seems to work quite well, and I think what we'll now do is take the circuit from the breadboard and build it on a little project board and into a box. Next thing we'll do, we'll use our little template to mark the holes for the top of the project box there, for the sockets, the on-off push button and the LED. So I have 1, 2, 3, 4 little crosses there which mark the holes for those. So what I'll do, I'll just prick them through with a little pricker, and then I'll drill the holes, and then we'll come back and have a look at that. So basically just holding the template on and then simply pricking the holes. The top now is drilled, the holes there for the banana sockets. That's the slot for the on-off push button, and there's the slot for the LED. So basically what I'll do now is I'll stick the front fascia on, and we'll cut away the holes through the front fascia there. Just peel off the and then position it over the top. Pierce the crosses there, you see, and then you simply just cut round to reveal the hole. Now there we have all the holes now cut out through the front fascia there, so we can now just have a look at mounting some of the components. I'll mount the sockets here first, and I'll just explain why I've chosen to put the sockets on this side rather than across the box. Now because we're using the metal plates, the aluminium plates as the front panel, we have to make sure that the 4mm banana sockets there are insulated. So the ones I have here, they've got plastic insulation there, which the plastic then slots through the metal. So basically what we do is we slot it through. Well, there you can see the banana socket coming through, and you can clearly see there the black plastic surrounding the metal terminal of the socket there and insulating it from the metal case. And then you have a small plastic insulator clip that goes on top, and then on top of that we put the nut. So it's completely insulated from the metal case, and then we just screw the nut down and tighten it up onto the front panel. So I'll just do the other one now and then we'll come back and have a look at it. Banana sockets now firmly fixed onto the front panel, and as I said, the reason I positioned them at this end of the box is I wanted to keep the sockets at this side, and that's the reason for that was that I'm using this 9-volt battery holder, which I want to slot right on the bottom and fix there at that side, and then I've got this gap here where these sockets can then fall down into. I couldn't put the sockets across that way because once we have the battery in place, these two will actually hit the battery, so that's the reason why we have them here. And then this battery holder will be fixed on this side of the case in the bottom. I've now fixed the battery holder into the case. I've secured it by one small screw there. There's actually 3 fixing positions on the battery holder, but I've just needed to use one, and that one I just drilled a little pilot hole into the bottom of the case and then just tapped that screw into the bottom of the case, and it seems to be quite firm. You could even probably glue this on with super glue if you wanted onto the bottom of the case, but make sure you keep it on this side of the case, and this side here is free. Right, let's have a look at the prototype board which we're using in this box for the circuitry, because we need to make provision for the 2 banana sockets to come through it. So just screwed the little project board on top there with these 2 fixing screws, and as you can see at the moment, if that won't slot down because the banana sockets are protruding down, so I need to drill 2 holes there for these to come through. You can now see I've drilled the 2 holes through there, and it's sufficient for the banana sockets now to protrude through there, so the top panel will now just slot and sit on nicely. The next thing we need to do is position the LED and the small tactile push button on the project board there, making sure that it comes through the front panel slots there. So basically what we do for that is just slot the components in. There's the LED slotted in, and slot the little tactile switch in, just hold it in place, and then simply the little prototype board, while you're holding these components, you can slot that on the back and position it. So the next thing I'm going to do is I'm going to solder the tactile switch on and solder the 3 leads of the LED so they're fixed in position at the right height for the board there. So we've got the same spacing at the front and at the back. And then once I've done that, I can remove the board, taking the nuts off the banana sockets, and then I can mount the other components on the board. Both the LED and the tactile switch are now soldered onto the board, so that holds the whole unit now quite firm. And so I can work on the board now. I'm going to remove the 2 nuts there, remove the board, and then mount the other components on that board. Right, we'll just work out now how we're going to mount the other components onto this board. The first thing obviously is the IC on its little board. That needs to be mounted somewhere around there, so it's near the output sockets, so I'll probably position it somewhere around there. And then we have the MOSFET, which is doing the switching, so I'll probably position somewhere around there. The circuitry for the LED, including the transistor, is going to probably slot somewhere around there with its Zeners and its resistors. So that's just give you an idea of how I'm going to position the components on this board. What I will do, I'll position them on the board, and we'll just solder a few in and then come back and have a look at what I've done. Right, there we have now all the components mounted on the board. You can see, as I mentioned earlier, there's the MOSFET, and there's the chip on its little adapter board there. The circuitry around here, as you can clearly see, is all to do with the little battery monitor circuit, So there's the transistor. You can see there the two 5.6 volt Zeners, and these four resistors here are all the 1K resistors. On this side here, the two capacitors there, a little tantalum and a little 0.1 microfarad capacitor there. That's on the input of the reference IC, and you have a little 0.01 microfarad capacitor on the output of the reference IC. The two resistors here, there's the 10 megohm next to the MOSFET. That's the capacitor there linked with the MOSFET, and then you have another 1K resistor there which is feeding the little tactile switch there in the center. So that's all the components mounted on the board. I'll just reverse the board and let you have a look at the other side. There's the underside of the board there, and you're just running the solder across the pads there on the project board. That strip there going down there is just simply the ground of the circuitry, and the red wire there and that section there is the positive supply coming from the MOSFET there. And then I've got the two connections here, the black one and the red one there. That will go to the two output sockets, the two banana sockets. So what we'll do next is we'll mount the board back onto the front panel and bolt it down, and then we'll have to solder these two wires onto the banana socket terminals. Right, there we have the board now firmly fixed onto the front panel. The banana sockets are now bolted down onto the board, and I've soldered the flying leads there onto the red socket and onto the black socket there. So that is now a complete assembly. So the next thing to do is connect the battery wires from the box, so let's have a look at that next. Here's the unit with the battery flying leads there. I've now soldered onto the board there. This red one is going to the connection on the MOSFET, and the black one is going to this earth-in line here. So the next thing I'll do, I'll pop the battery in, clip the battery in. And then what I've also done is I've just cut a little bit of card out there just to put on top of the battery, just to be on the safe side. There's actually a little distance between the battery and the printed circuit board, but just to make sure that nothing shorts onto that. So a little bit of insulating plastic or card we can use for that. So I just took the wires down there, put the bit of card on top, and then we seat the whole unit then. Right, with the top now seated onto the box, let's just check before I screw it down. Let's just check that it's working. So if I press the button, the green LED should come on. There you go. It seems to be working fine. So what I'll do now is I'll just prick in the corners where the screws go in. And then we'll put the fixing screws on the front panel. So there we have the finished unit, all now screwed on at the top there. Just a little word of caution: when you're putting the screws in, I found it a little better to just cut out the top of the fascia there where the screws go before I put the screw in. Otherwise, it tends to tear the front fascia. Right, so the next thing we'll do is we'll give it a final test. Here's the final unit. I've got the leads plugged into the meter here, so let's just switch on and check the reading coming out. There we are, 5.00006, and you see the green LED light is on. After about 2 minutes, the unit goes into auto switch off and the red light just glows for a few seconds and then goes out altogether. So that seems to be working fine. Well, I hope you found that little project today of designing and building a 5V reference standard of interest. Many thanks for watching. If you found it useful, please give us a thumbs up, and see you all again next time. Bye for now.